Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning, everyone. Today we will examine lake ecosystem dynamics with a focus on how nutrient cycling interacts with thermal stratification to shape biological and chemical conditions in lakes. To begin, I want to define stratification. In summer, many temperate lakes develop three layers. The warm upper layer is the epilimnion. Below that is the metalimnion or thermocline, where temperature changes rapidly. The cold, deep layer is the hypolimnion. Stratification controls mixing, and therefore oxygen distribution. The epilimnion exchanges gases with the atmosphere, and usually stays oxygenated. The hypolimnion can become isolated, and, if decomposition of organic matter is high, it may become anoxic by late summer. Nutrient cycling interacts with these layers. Phosphorus and nitrogen enter lakes from watershed runoff and internal sources. During stratification, nutrients can accumulate in the hypolimnion, because limited vertical mixing prevents them from reaching the surface. An important mechanism is internal loading. When bottom waters become anoxic, chemical conditions at the sediment-water interface change. Under low oxygen, iron cannot bind phosphate as effectively, and phosphorus is released from sediments into the hypolimnion. When the lake mixes in autumn or spring, that phosphorus can be transported into surface waters where light is available, and phytoplankton can use it. For example, in Lake Mendota, researchers observed pulses of phosphorus after turnover that stimulated late-season algal growth. This explains why reducing external phosphorus inputs alone sometimes fails to eliminate blooms quickly. Internal loading can sustain productivity for several years, until sediment stores are depleted, or until management targets the sediment source. Another concept is holomictic versus meromictic lakes. Holomictic lakes mix completely at least once a year. Meromictic lakes have deep waters that rarely mix. Meromixes can lead to permanently anoxic deep zones, and long-term accumulation of reduced compounds and nutrients. Light and primary production are also influenced by stratification. The epilimnion is the productive zone but is limited by nutrient supply. If nutrients are trapped below the thermocline, primary production in the surface layer may be nutrient limited despite high light. Climate warming alters these dynamics. Warmer surface waters intensify stratification and lengthen the stratified season. That leads to longer periods of hypolimnetic anoxia, and potentially greater internal loading of phosphorus. We see this pattern in Lake Erie, where stronger thermal stability in some years has coincided with larger cyanobacterial blooms. In that case, agricultural phosphorus loading and stratification interact to amplify blooms. Management strategies, therefore, must consider both external and internal nutrient sources. Options include reducing watershed phosphorus inputs, aeration or oxygenation of bottom waters to prevent anoxia, and in some cases sediment capping or dredging to remove nutrient-rich sediments. A useful field approach is to monitor temperature profiles and dissolved oxygen profiles regularly. Sudden changes in oxygen in the hypolimnion can indicate onset of internal loading risk. Coupling these observations with nutrient measurements helps predict bloom likelihood after turnover. Finally, remember the coupling between physical and biogeochemical processes. Stratification sets the physical template. Nutrient cycling and biological responses fill in the ecological outcomes. Understanding both is essential for effective lake management and restoration. In summary, thermal stratification controls mixing and oxygen distribution, which in turn influences internal nutrient cycling. Internal loading of phosphorus under anoxic conditions can fuel algal blooms after turnover and complicate restoration efforts. That ends the main part of the lecture. In the next session, we will examine specific monitoring techniques and a case study of a lake restoration project.
Listen again to part of the lecture, then answer the question.
When the hypolimnion becomes anoxic, phosphorus is released from sediments and can fuel algal blooms after turnover.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.